So last time we had talked about making an impression in this process of making a crown. So we talked about pushing the tissue away, using some polyvinyl siloxane to get a good mold of our tooth so that we can then go ahead and make a crown that's going to fit on top of it. So this slide here just runs through some of the lab procedures needed to finish off this crown. So the focus of this lecture is going to be going over the rest of these steps and also the dental materials that goes along with it. So there's going to be a long list of things that we're going to be using in order to fabricate our end product, which is a crown. So the next step in making a crown is once we have our impression, we're going to pour that into some sort of dental stone. Once that stone sets up, that is our replica of what our tooth preparation looks like. And from there, we're going to build the crown using wax. So that wax pattern that we wax up is going to be in the same contour of what our final crown is going to look like. And this wax is going to be able to be removed from the die so that we can put it in this investment material. So basically we're going to attach a sprue and then embed this wax pattern into the investment material so that when we go ahead and heat up this whole crucible, the wax pattern is going to get burnt out, and what you're going to be left with is just a big void of space that looks and is in the shape of a crown. So just to clarify, this sprue here is also made of wax. So this whole thing, once it's burned out, is going to be essentially just a void. And in order to make the casting, what we do is just melt down a bunch of metal, and then that gets slung into this empty space, and then it'll fill this void. And then as a molten metal cools down, then that's how we get our crown. So eventually cut off the sprue, do our finishing and polishing procedures, and then our crown will be ready for delivery into the patient's mouth. So yeah, let's get into this next step of pouring this impression into stone. So just in our little timeline here, we call this sort of the mounting step. It encompasses several different steps. The first of which is to turn that impression into stone. So let's talk about dental stone for a second. Another word used is gypsum. That's going to be the generic term for it. And this is something you've used a little bit before, where you've made alginates and poured that into our type 3 microstone. So essentially, if you were to boil down the chemical reaction, it's powder, and you mix it with a little water, and then a few minutes later you get this hardened stone, and if you notice, it'll also produce a little bit of heat as it sets. Okay. So the chemical formula is going to be Hemi Hydrate, so you can see that down here, and that mixes with water to form this dihydrate plus unreacted hemihydrate plus heat. Okay, so here's this kind of a more lengthy description of sort of the details in terms of how this dental stone will set. Really, the main concept I want you to remember is that this follows a dissolution precipitation theory. So basically, as water starts to mix with the hemihydrate, it forms a precipitate, and those precipitates are then grow sort of like crystals. As they grow, they get bigger and bigger and bigger, and then that crystal structure is what kind of hardens the stone and gets it to its full set. Okay. When we talk about dental stone, there's going to be several different types that we talk about. So if you just look at this chart, the way that dental stone is classified is by its compressive strength. So you've used this before. This is our mounting plaster. Sometimes it's called an impression plaster. But that's our lowest strength stone. So that's a type 1 stone. And on the other end, we have a type 4 and 5 stone that are considered high strength. So just looking at the megapascals of compressive strength, that is how we're going to divide up or classify our dental stone. You'll notice that types 4 and 5, they share the same compressive strength, but they are further differentiated by the type or the amount of expansion. So type 4 is called low expansion, and type 5 is called high expansion. And as we get into the rest of the casting process, we'll explain to you why there's a difference between types 4 and 5. But the main point of this is know that gypsum is classified by its compressive strength. Alright, so just a little bit more about this plaster or gypsum. Type 1 and 2 is often referred to as plaster, whereas types 3 to 5 are referred to as dental stone. So the thing you have to remember about this gypsum is that if you look at the particle size of plaster, they're actually classified as a Hemi hydrate. So the beta Hemi hydrate. So beta Hemi hydrates are large, irregularly shaped particles of gypsum. So when you get it in the powder form, it's going to look, or if you zoom in on the powder form, it's going to look like these large, irregularly shaped structures, and that's called beta Hemi hydrate. On the flip side, when you look at types 3 to 5, these are going to be considered alpha hemihydrates. So they're much smaller in particle size, and they're prism and rod shape. So this kind of makes sense in the sense that if you think about type 3 to 5 stone, remember they're the higher strength stone that we have. So if you have smaller particles that are more regularly shaped, then obviously they're going to pack in a little bit more densely. So if things are more dense, then that's going to be a higher strength stone once the crystals have formed and you've come to a full set. So here's just a list of the 5 types of stones, and just a brief overview for common applications. Type 1 is generally going to be used for mounting our casts together. So that's just attaching our cast of interest to our articulator. So that's something you've done in your D1 year. Type 3 is our stone that we're going to use when we make dentures, and also when you get down in the clinic, what we use for our diagnostic casts, also known as study models. If we just want a idea of what the patient's teeth look like, we'll pour up some study models, but we generally don't use this to fabricate any fixed prosthesis that have to do with crowns and bridges. This is mainly going to be used for fabrication of dentures. Okay, so type 4 and 5, these are the type of stones that we're going to use when we start to make our fixed prosthesis. For a few reasons. One is that, or for the main reason, in the sense that they're high strength. So you can imagine as we're making and going through all these wax ups and castings and adjusting contacts, we're trying on and off the crown multiple times onto this stone. So we want something rather strong so that's going to resist abrasion of the stone cast. So again, the stone cast is a representation of what the patient's mouth is like. So we want that stone to be relatively undisturbed so that when we make and adjust our crown on the cast, it's going to be accurate when we put it in the patient's mouth. So this chart just signifies the principle of water to powder ratio. So if you were to think about it, our type 1 stone, remember that's beta hemihydrate. These are large, irregularly packed particles. So it would make sense that it would take more water for that to mix together, because of the irregularly shaped particles, you're going to have a lot more space between them. And if you were to contrast that with type 5 stone, which is smaller, regularly packed particles, well, there's not as much room for water to fit in between those particles. Let's look at all the dimensional changes that occur between all the materials that we use. So impression material, well, that's a polymer, and we know polymers, when they link up together, those shrink. And then we're going to pour this impression into stone. So stone will expand. We're going to make a wax pattern, and then we're going to embed that wax pattern into some sort of investment material. So this investment material also expands under setting. Now when we talk about metal, we're going to heat up the metal really hot, but once we sling it into this space, guess what happens? It's going to cool. And in this cooling, this metal is actually going to shrink. So if you think about all these steps, we have all these different materials that shrink or expand at different rates. Well, over time, our dental lab technicians have really fine-tuned the amount of expansion and shrinkage of this material. And what happens is that since each material goes under a different amount of dimensional change, we want to be able to control how much that changes to get a restoration that requires a minimal amount of adjustment. So over time, our lab technicians have figured out the setting, expansion, or shrinkage rates of all these materials so that they know what combination of materials to use together to get to a restoration that's going to have a minimal amount of adjustment. So if you think about all the different changes, well, if some expands but some shrinks, at the end you want a net zero effect essentially by the time you're done with your crown. This is why I emphasize this point of being real careful with your water powder ratio. These are measured out real carefully so that you don't disturb the amount that you expect it to expand, because otherwise it may throw off the rest of the fabrication process. So at our school we use a type 4 high strength die stone for our crown and bridge work. The other important thing is that we end up vacuum mixing our stone. So this is just a picture showing the difference between two casts that have been poured up. One has been vacuum mixed, and this is a much more uniform mix. You're not going to have any air bubbles that may weaken the stone. So this definitely reduces the porosity of it. So if you can think about having air bubbles within the cast, that may lead to inaccuracies, especially if it's at the surface level. All right, so once we have our stone cast poured and set, well, we need to connect these casts to an articulator. So this series of photos just depict the process of doing that. So we have a cast here that we're going to attach with plaster to the top member of the articulator, and then once that is set, well, we need to somehow relate the lower jaw to the upper jaw. So we call this part that when we put the two casts together, our jaw relation. We want to do this to simulate the patient's bite in the way that they close down. So if the patient has a stable maximum intercuspation position, it's as simple as hand articulating the two casts together so we get a stable bite. Once we do that, a lot of times we'll lute those together so that there's no movement, so that when we add plaster to the lower, it'll be really stable. So mount the upper, we'll relate the two jaws together, and then mount the lower to the articulator. So here's just a picture of a completed mounting for a single crown case. We have our master casts, which are in type 4 stone, and then they are mounted to the articulator in a type 1 stone. So let's talk about this concept of a byte registration. A byte registration is a record that's made in the mouth with a fast setting PVS material. So what we do is we squirt this material over the crown preparation, and then we have the patient bite down. So this byte reg serves a couple purposes. One, it helps to verify that the casts are seated together in the right orientation. The other thing that it can help us do is in certain situations, this byte registration is going to help stabilize the cast and prevent any rock, especially if you're not able to hand articulate it well because it doesn't form a tripod. So you can see here that the byte reg is trimmed here so that we can confirm that our casts are seated in the right orientation. So let's take a look at what happens after we've made the byte registration in the mouth, and then we go use it to help us mount our casts together. In this particular situation here, we can see that the byte reg is not trimmed yet. And because it's not trimmed, you'll see a gap between the registration and the stone casts. Well, obviously this probably isn't an accurate depiction of what's going on. So in order to solve that, we actually want to trim this byte registration to avoid any interference. Okay, so let's talk about why this happens and why we really need to trim this registration. So here, this is going to be an example of the patient's mouth. And what we do is we squirt this registration material intraorally, so it picks up the detail of the teeth here. And on the other side, we don't show it, but this side should be contacting, or the bottom side should be contacting the prep tooth. So this is made intraorally, and then we set that aside for now. But as you know, we make a impression of what the teeth look like. And with that impression, we're going to pour that into stone. So that's what this blue represents, is that this is the stone cast of what the teeth look like. So I'm going to highlight this here, but if you look real closely, what I'm trying to simulate here is this idea that when we go from the patient's actual mouth to the stone cast, notice how the detail of all the grooves and embrasure spaces change. So when we go from the real life example to stone, we know that not everything is perfectly replicated. In fact, we miss out on some of the detail that's actually in the mouth just because of the limitation of the impression material and the stone. It doesn't 100% perfectly replicate what's in the mouth. So when we try to put this PVS registration that is extremely accurate, well, this picks up a lot of the surface detail. So when we go put that and try to seat that together, the detailed portions of that PVS obviously isn't going to fit into the stone replica of what the teeth look like. So in doing so, you're going to find a gap between the registration and the stone cast, just like we saw a little bit earlier. So really the solution to this is, well, let's trim the record so that the only part that really touches are going to be these cusp tip areas. So once we trim sort of the embrasure spaces and start to flatten it out, well, now everything that wasn't picked up in detail won't interfere because we've trimmed off this registration. So as we now go to seat this registration, we can see that this will actually fit more accurately. Okay. So this is just a picture showing how we trim it, and basically all you want to be left with is these cusp tips. Notice how the embrasure spaces here that it captures the fine detail and that really sharp V shape. We trim those down because we don't want that part to interfere with our stone. The other principle that I want to draw your attention to is the fact that we actually want to trim the registration anywhere where tooth meets tooth. So in this example, we can see that these are the prep teeth, but here we actually had mistakenly picked up a little bit of the contact between this tooth and then the lower tooth. And you can see a little perforation there, signifying that those teeth actually came into contact with each other. So we don't want any impression or PVS material in between two teeth that are actually in contact, because again, that may prevent that registration from seating down all the way. It's better to leave it stone on stone contact as opposed to having stone to byte reg to stone. So you always want to trim that part off. So this next concept that I'm going to get into about byte registration may require just a little bit of imagination for you to visualize what's actually going on here. You may have to watch this part a few times to get a good grasp of what's going on here. So sometimes we have a situation in which we need to mount these two casts together to make a crown, but we're missing several teeth. So in this case we have a full complement of maxillary teeth, but you can see that we're missing teeth in the posterior here. So the slide here just depicts the fact that if you don't have teeth here to stabilize it, well, you're not exactly sure how you're supposed to mount these together or what orientation in which they should be in. Should it be have a lot of space, a little space, or something in between? So we have to come up with a way in which we can accurately mount these casts together so that when we make a crown, it's going to be in the proper occlusion. So the way around this is we have to, once our cast has been poured up, on the stone cast we have to make this thing called a record base. So a record base basically is just made out of this acrylic material and wax. So if you want to think it this way, this is sort of just a placeholder for teeth. Remember, if we had a full complement of lower teeth, well, we generally don't have an issue because we have a tripodized contact in which we can mount this stably. So this is just sort of a placeholder. So what we do is after we make this record base, well, we place this into the patient's mouth. And then we ask the patient to close down, and while they're closing down we're going to inject some of this byte registration material, very similar to what we had seen in the prior example, except instead of having it contact tooth to tooth, now it's contacting maxillary teeth to a lower record base, which is again made out of acrylic and wax. So once a patient closes down into that, we now have a record of how much space is in between the upper jaw and the lower jaw. So with this record we can put it back onto the stone cast here and now have an accurate and appropriate mounting so that we know exactly how tall we need to make this particular crown here. Okay, so this is the just a slide showing the case mounted correctly because we had used the record base to capture the amount of space that actually exists in the patient's mouth. So here we have the two types of registration material that we have in our clinic. We have Regisil, which comes in purple, and then Take One, which is in green. Let's explore Regisil first. Regisil has a longer working time. It's 1 minute 10 seconds, and it's not as rigid as the other Take One material. So the longer working time has its place, especially when you're trying to get a byte registration of multiple crowns that you've prepared. So let's say you have crowns on both the left and right side. Well, sometimes it takes a little while for you to inject all this material, so having a longer working time helps out. The downside, though, it's not as rigid. So let's compare that to Take One. Take One sets up extremely quickly. It'll set up in about 30 seconds. But this material is much more rigid. So if you think about our mounting procedure, well, we want to form a stable byte that's not going to rock. So the more rigid that your byte registration material is, the better, because you're not going to have a bounce as we put the two dental casts together. Alright, so as we continue down this crown fabrication process, our next step is the die trimming part. So as you remember from the video, we need to remove the stone that it's just beyond our crown margin. So if you remember from our impression step, one of the critical things that we're trying to do is to push the tissue out of the way so that we can get impression material beyond the margin and a little bit onto the root surface of the tooth. The reason for that is it makes this part of the procedure so much easier when you have a large separation between where your margin is and where this excess stone is. So trimming the die is probably one of the more critical things that you can do or that we need to do in terms of accuracy and getting a good seal of this crown. If you think about the fit of the crown, well, this margin becomes the most critical part because that's where the crown meets a tooth, and we want to minimize the gap there so that no bacteria or anything can get in between there and form a cavity underneath. So we're looking for a well-sealed margin, and a well-sealed margin starts with a nice clean crown prep, nice smooth margins, and a nice impression that captures all the surface detail to it, and then also a nicely trimmed die so that we can accurately see exactly where that margin ends. So in order to help us see that more clearly, once we have it die trimmed, we're going to mark that margin with a red pencil. What we also need to do too is to add die spacer onto the preparation, and the reason for that is we need to leave a little bit of space for our cement. So if you think about, if we made a crown that fits the tooth so snugly that there's not room for anything, the minute that we put cement into that crown and try to seat that, we're not going to be able to have that crown go down all the way, because the cement is going to take up some minimum film thickness. The cement can only get so thin, so therefore we need a little bit of relief or some space in between our tooth and our crown. Once the die has been prepared, then the next step would be to add wax. So you add wax, and then you basically shape it into the shape of the tooth that you want. You'll end up checking the interproximal contacts as well as the occlusal contacts to make sure that everything is contoured the way they're supposed to be. You're also going to verify that the wax pattern seals the margin accurately. If you're doing a porcelain fused metal crown, you're going to provide a cut back of this wax. Basically, you're going to cut it back a certain amount so that you make room for the porcelain. If you're making a full gold crown, then obviously this is going to be to the full contour of what that final crown should look like. One of the important things to keep in mind is the absence of an undercut. So remember, if you have an undercut within your preparation, it's at this step here that your wax pattern is not going to be able to be removed, or it'll break. So the undercuts would prevent us from removing the wax pattern. This is when you'd find out if if an undercut is going to be unacceptable to us. So once the wax pattern is made, we need to invest it, and what we do is we attach a sprue, which is also made out of wax, to the largest non-critical part or cusp of our tooth. So the reason we put on a non-critical cusp or non-functional cusp is because eventually we're going to have to cut the sprue off. So I don't want to mess with any of the surface that is going to be affecting our occlusion. Okay, so this gets attached, and we put it in this crucible former, and we're going to fill this area with investment material. So it's going to capture what this wax pattern is going to look like. So the reason we need to do this and have a sprue attached is that we need to make a little reservoir for this metal to flow into. So some of the times, especially when you're doing a larger casting, they also have these runner bars inserted in there. So this creates a big reservoir of molten metal that's going to allow us or it's going to allow the metal for it to flow into. What you don't want to have happen is for the metal to cool first here and not have enough molten metal to get into all the spaces at the edge of our crown. So generally our margin is going to be the place furthest away, and if you don't have enough molten metal, it's not going to be able to fill our wax pattern completely. So something else I want to describe is this idea of suckback porosity. So remember, we're trying to control the temperature of how everything cools and heats. So what we're looking for is for this part of the crown to solidify first, and then have the solidification of the metal run from the top down. Now, if you don't position your sprue correctly, or if something goes wrong in this casting process, sometimes what's going to happen is the parts away from your margin is going to cool first. Well, when this happens, all this molten metal here is going to suck back towards the area that had cooled first, and then you're going to end up with voids within the casting. So you can see how the our casting is short of our margin as compared to the one here, and you can see a large void in this surface here when it should really look like this, and that's because this portion of the casting had cooled first and then created this suckback porosity. Alright, so let's talk about the investment material, or the material that we're going to use to encase this wax pattern. We're going to classify this into three different categories, and the classification of investment material is based on its binder. So if you look at the composition of investment material, the two things that I want to highlight is the fact that investment material is made up of two components, the binder and the refractory. So these are going to be two key points that you're going to remember, because these are going to be good test questions for us. Okay, so investment is classified by its binder. We know that there's three types: gypsum, phosphate, and ethyl silicate. And the purpose of the binder is to provide rigidity to this investment material once it solidifies. What's also contained in this investment material is a refractory material. And specifically, this refractory material is made of silica. So the refractory material regulates the thermal expansion of this material. So remember, in the beginning we had talked about the fact that each material has either expands or it shrinks. Well, we want to control the amount that this investment material will expand so that it's in harmony, or it's compatible with all the other steps, so that by the time we get to the final restoration, we have a net zero effect. So going back to the slide, we're going to start off talking about the phosphate bonded material. This is the material that is generally used nowadays in dentistry. This can be heated above 650 degrees Celsius. Remember, this part needs to be put into a burnout oven, because once this investment material has solidified around the wax, well, we need the wax to disappear so that the molten metal can flow into it. So we got to put it in a really hot oven for the wax to essentially vaporize. So this is allowed to be heated above 650 degrees Celsius. Previously, gypsum bonded phosphate material were really popular because they tended to capture a lot of the good surface detail. While these dropped in popularity because of the fact that they couldn't be heated above this 650 degree threshold. The metals that were used in the past used to melt at a much lower temperature. So before the price of gold got very expensive, most of the dental materials, or the dental alloys or metals that were used in dentistry, were of a high gold composition. So since there's so much gold in it, gold melts at a much lower temperature than some of the other metals that are being used today. So this allowed them to use this gypsum bonded material because it melts at it didn't need to withstand a high temperature, and also for the fact that it captured a little bit better surface detail. Okay. The last category of investment material is the ethyl silicate. And really the only thing I want you to know about that is this investment material is used for our partial denture frameworks. So in our previous lecture we had talked about the need for survey crowns. Well, the removable partial denture, the actual denture itself has a metal component to it that hooks on to the survey crown. Okay, so this metal part in the previous photo we had shown the metal clasp. That whole complex is made out of a base metal, and in that particular metal they're going to use an ethyl silicate investment material. Alright, so let's wrap up with metals here. So in this first slide here, I just have a chart showing you various compositions of metals that are used within dentistry today. So I just want you to get appreciation of the fact that the metals that we use aren't just a single metal, but rather they're an alloy or a mixture of several metals in differing proportions. So here's just another chart that shows popular combinations of metals and the percent composition of each type of metal. Okay, so you have some gold, silver, platinum, etc. So I do want to talk about how dental metals are classified. We have this concept of noble metals. So there's 7 noble metals in dentistry, and they're listed here. So the advantage of using a noble metal is the fact that they're really resistant to corrosion. So if you think about a noble gas from your chemistry class, those are really stable gases. So in a similar idea, noble metals tend to be very unreactive. And that's good when, especially when you're putting this metal in somebody's mouth. You don't want this metal to, or this prosthesis to undergo a lot of changes or corrosion in the mouth. So let's talk about how we're going to classify these dental alloys. So if you remember, our dental alloys are composed of various metals that are put together. So if you, for example, if you were to look at these charts, you would find that this particular alloy has about 47% gold, 40% silver, 7% copper, 4% palladium. Okay, so we need to know those percentages because that's going to help us determine whether they are a high noble metal, or a base metal. So for something to be classified as a high noble metal, these two conditions must be true. So the first one that we're going to look at is 60% of the metal composition needs to be of noble metal. So remember there are 7 noble metals or 7 metals that are considered noble. If you were to add up the percentage of each in that particular alloy, that needs to be above 60%. And in addition to this criteria, we are then going to look at the gold composition just by itself. If that metal has more than 40% of its composition is gold, then those two conditions, if they meet, then they would be then that alloy would be classified as a high noble metal. Okay, so if that condition is not met, then we would check this next category of noble metal. Well, does this metal or this alloy contain 25% or more of noble metals? So remember here, this is just one criteria. It doesn't have this gold criteria on its own. So if it fulfills this criteria, then we would consider it a noble metal. Um, if it doesn't fulfill this criteria, then we would consider this or that particular alloy a base metal. All right, so if we're to compare two extremes, let's just take noble metals versus base metals, right? So noble metals have high percentage of noble metals, which are really stable. If we're to compare the two, we have 5 different categories of material properties that I want you to think about. So let's talk about melting temperature first. So we know that gold, which is a noble metal, has a relatively low melting temperature. So it makes sense that noble metals melt at a lower temperature than base metals. Then let's talk about shrinkage upon cooling. There's going to be less shrinkage of noble metals on cooling than base metals. So remember when we looked at gypsum, we had talked about type 4 and 5 gypsum, where they're both high strength stones, but one is low expansion and the other is high expansion. So just keep that in the back of the mind. So if we think about high noble metals versus base metals, we know that the base metals end up shrinking more upon cooling when compared to the higher noble metals. So if you think about the difference in shrinkage, what's a good way to compensate for that? Well, you can compensate it by using a different type of stone when we use a base metal which shrinks more. So oftentimes what you're going to find is labs that end up using base metals for their crowns, they'll use a high strength, high expansion stone to compensate for the fact that the base metal shrinks more. So if you have a stone that expands more, it'll compensate for the metal that shrinks more to get that net zero effect. Castability is just the ability for the metal to fill in that wax pattern of the void in that investment material. So we're going to say that the high noble metal has better castability. Okay. In terms of hardness, just think of gold. Gold is a softer metal, so you're gonna say that noble metals have decreased hardness compared to a base metal. And when it comes to corrosion, we know that noble metals are pretty stable, so those are going to be less corrosive to when you compare it to base metal. So let's talk about castability here. This is just a diagram showing how they measure castability. So they made a wax pattern of sort of this mesh, and then they were trying to determine which metal can fill in and really cast all the little detailed structures of this mesh pattern. And what we find out is that the gold or the noble metals, noble alloys, tend to have better castability and are able to fill in with detail this whole mesh network here, or this whole mesh casting here. So this is just a different type of study that they did, where they casted a bunch of different crowns with the various metals, and they were measuring the marginal discrepancy after casting. So these are casting accuracies. So on the lower end, these are going to be your high noble metals. So you can see that these are gold and platinum, palladium containing. And as you got to the higher marginal discrepancy levels, you can see that these are base metals.